In 9.1, we're going to be looking at sequences. So I'm just going to go through a few of the homework problems or similar problems. To begin with, there are different ways of establishing sequences. A sequence is just a list of numbers that have some type of pattern to them. So one way of describing a sequence is with a formula like this, where the first term we use a 1 for n. The second number in the sequence we use a 2 for n. The next number in the sequence, of course, we'll use the next integer. And one thing to note is that in integer or in sequence formulas, n is always an integer. But there are different ways of expressing. This is one way to describe a sequence, but we can also describe sequences what's called recursively or other names for it. We can denote the first item in the sequence, and then we can say, well, each following item is one, for example, 1/3 the previous one squared. So this notation means my new element is going to be the previous element. K is the one before k plus 1. So my new element is going to be 1/3 the previous one squared. Or we could have one where we say, let's start with 2, and then each subsequent one is going to be 3 times the previous one to the third power divided by 5. Just when they're described recursively or recursively defined means they're defined based on previous values. So if we do the one on the left, A1 is 6, A2 is 1/3 A1 squared, so 6 squared, that's 36 divided by 3. A3 is 1/3 12 squared, so 1/3 times 144, or 144 over 3, 48. Then A4 would be 1/3 of 48 squared, and so forth. So our sequence is 6, 12, 48, and then our next number. So that's just establishing a sequence, using a formula to describe a sequence of numbers. This is a different way of using a formula to describe a sequence. So some of the problems you'll be given a sequence of numbers, and you'll be asked to find the next so many numbers in the sequence. So the key is just going to be in determining, well, how do we get from one value in the sequence to the next? So notice from here to here, 5. From here to here is 5. There to there is 5. So to get to the next number in the sequence, we just add 5. So the next value would be 33, and 38, 43, and so forth. So it's just describing a pattern. Let's look at another example. Let's look at 6, -2, 2/3, -2/9. So in this one, you may notice, okay, from 6 to 2, that's a difference of 8, which is not the same difference between those or those. So the way we get from one to the next is not by adding or subtracting amount in a certain amount. Also, you'll notice our signs alternate. One thing that you may notice that, especially on the last two, our numerators staying the same here, but our denominator is getting larger. How do you get from 6 to negative 2? Well, if we divide 6 by 3, we get 2. If we divide it by negative 3, we get negative 2. Notice if we take negative 2 and divide it by negative 3, two negatives make a positive, giving us 2/3. If we take 2/3 and divide by negative 3, or rather, 2/3 times negative 1/3, positive times a negative gives us negative 2/9. So to get from one step to the next, you can look at it as either dividing by negative 3 or as multiplying by negative 1/3. So from here to get to the next one, multiply by negative 1/3. That'll give us a positive 2/27. To get to the next, multiply by negative 1/3. That'll be a negative 2/81. And you could continue that sequence as long as needed. The next little section is dealing with simplifying factorials. And eventually we're going to be doing some things involving some factorials. So let's look at simplifying something such as this. And remember that a factorial, if I have 5 factorial, that means 5 times 4 times 3 times 2 times 1. You just start at that number, multiply all the way down. So n factorial means n times the next smallest number, so n minus 1, times the next smallest number, n minus 2, times n minus 3, so forth. N plus 2 factorial means n plus 2 times the next smallest number. One smaller than that would be n plus 1. Take 1 away from that, and that would be n. Take 1 away from that, that would be n minus 1, n minus 2, and so forth. And depending on what n is, then you're eventually going to get all the way down to 1. Now you may notice that once you get to a certain point, both of these have an n minus 1, both of them have an n, both have an n minus 2, both will have n minus 3's, and they'll have all the remaining factors the same. So we can simplify this and get 1 over n plus 2 times n plus 1. Often you'll see this written. Let's look at some factorials that have numbers instead of letters. Let's rewrite this as 7 times 6 times 5, and then it'll be times 4 times 3 times 2 times 1. But since the denominator is 5 factorial, instead of listing 4, 3, 2, 1, and so forth, notice that 5 factorial would take care of the rest of those. So 5 factorial times 6 times 7 is 7 factorial. Well, if I've got 5 factorial on top, 5 factorial on the bottom, those take care of the same factors. So those cancel, leaving us 7 times 6, or 42. We'll look at another example, 2n plus 2 factorial over 2n factorial. Let's take the largest one and break it down until we get to the level of the smallest one. What do I mean by that? If we expand the numerator, that's 2n plus 2 times the next smallest integer, which would be 1 less. So if we take 1 away from this, that'd be 2n plus 1. The next smallest one would be 2n. And notice the numerator and denominator will have from 2n on down the same. So instead of writing any more terms, from 2n on down is 2n factorial. So those cancel and those cancel. So that's 2n plus 2 times 2n plus 1. So that's an expression that actually doesn't have factorials in the final answer. That is a simplification of this. Then there are a few where asked to find the limit of a sequence. If we have a sequence defined in this manner, and we're asked to find the limit of that, just think about the first term is 6 plus 2 over 1 squared. The next term is 6 plus 2 over 2 squared. The next one is 6 plus 2 over 3 squared. Then 6 plus 2 over 4 squared. So if we take the limit of that, as n goes to infinity, then notice the first part is staying the same, but as n goes to infinity, the denominator on the second one is getting bigger and bigger and bigger. So that term is going to 0. So that limit is 6 plus 0, or 6. So just take the limit in the old-fashioned way. One thing that might be useful on some of these limits is theorem mentioned in this section. It basically says if the limit is x goes to infinity of a function, that limit is L, then if we have a sequence that is equivalent to that function at values at integers, difference between this function and this sequence is that a function, the domain is continuous. But for a sequence, n is just going to be integers. So, for example, if I have the function, f of x equals x squared, the corresponding sequence would be a sub n equals n squared. This function is defined at any real number. This sequence is only used for natural numbers. So one of the theorems says if the corresponding function has a limit of L, then the sequence will have that same limit. So if we have some sequence that's messy, we might need to use something such as L'Hopital's rule. L'Hopital's rule applies to functions that are rational. Remember, if we take the limit as x goes to a particular number of a rational expression and we get something that's indeterminate, then we can take the limit as x goes to that value of the derivative of the top over the derivative of the denominator. So if we have a sequence that is indeterminate, as n goes to infinity, then we can think of it as a function, even though we're only actually using integer values to plug in. And we can apply L'Hopital's rule to that sequence as we take the limit. Now, after we kind of introduce sequences and look at limits of sequences, then in the last section of the last chapter, we talked about convergence and divergence. And in the last section, when we took the limit, if it went to infinity, it was said to diverge. If it went to a specific number, it converged. And in a sense, that's what we are going to do here. But it's a little bit, there are other cases for divergence other than things just going to infinity. If we have a sequence, let's say 1, negative 1, 1, negative 1, 1, negative 1, that's a sequence. To get from one step to the next, we basically multiply times negative 1. But notice that's not going to any particular value. It's bouncing back and forth between positive 1 and negative 1. If we kind of plot that where we plot n in the x direction, a sub n in the y direction, our first value, we get 1. Our second value, we get negative 1. Our third value, we get 1, then negative 1, 1, then negative 1. It's bouncing back and forth between 1 and negative 1 and not going to anything in particular, so it does not converge, thus it diverges. So something that converges is going to be something that's working its way towards a particular value. If we look at the sequence 1 over n, when n is 1, we get 1. When n is 2, we get 1/2. When n is 3, we get a third, a fourth, a fifth. And notice as we go, we're working our way closer and closer to 0. Now, for something to converge does not necessarily mean we have to get all the way to that value, but it's pretty much, it's similar to saying that the limit exists, or it's what the limit is. So this one, this converges to 0. And there are different properties mentioned throughout this section. One of them, we discuss the ideals of things being monotonic. Monotonic means that each subsequent value in the sequence is either getting smaller from one step to the next, or every value is getting larger from one step to the next. So we could say that A1 is bigger than or equal to A2. A2 is bigger than or equal to A3. A3 is bigger than or equal to A4, and so forth. That would be a monotonically decreasing sequence. Each value is getting smaller and smaller and smaller. A sequence that monotonically increases, the first value is smaller or equal to the second one, which is smaller than or equal to the third, which is smaller than or equal to the fourth, and so forth. So each value is either the same size or gets larger and larger and larger. So that would be a monotonically increasing. So if we look at a set or a sequence that does this, that sequence is monotonic. Every value is getting larger and larger, and it's increasing, so it's monotonically increasing. Monotonically increasing. Another idea dealing with sequences is the ideal of being bounded. Something that is bounded is restricted. For example, if we go back to 1 over n, each value is getting smaller and smaller and smaller. But notice those never get negative. So we could say that that's bounded by 0. It never gets below the value of y equals 0. We could look at another one. Let's say the sequence 2 minus 1 over n. If we look at that sequence, the first value, if we substitute a 1 in, we get 2 minus 1, which is 1. If we substitute a 2 in, we get 2 minus 1/2, which is 1 1/2. If we substitute a 3 in, we get 2 minus 1/3, or 1 2/3. If we substitute a 4 in, we get 2 minus 1/4, or 1 3/4. So those values are getting larger and larger and larger, but they're bounded. They're never going to get larger than 2. It's monotonic because each value is getting bigger and bigger, but they don't get bigger and bigger all the way up to infinity. They get bigger and bigger, and the largest value we could get is 2. So that's monotonically increasing and bounded. And one of our theorems says if we have a sequence that's monotonic, it's going either up or down, never both. If it's monotonic and bounded, then it converges. Now, that doesn't tell us what it converges to, but we can guarantee that it's something that is bounded, that is either always increasing or always decreasing, will converge. Now, this example is said to have an upper bound. This one is said to have a lower bound. If something is bounded both above and below, then it is just said to, in general, be bounded. So let's see if another theorem that might come in useful on some problems. Let's say we have some function that bounces back and forth. Sometimes it's positive, sometimes it's negative. Let's say it goes back and forth between being positive and negative, positive and negative. If the limit of the absolute value of that function is 0, or the limit of that absolute value of that sequence is 0, then the limit of that sequence without the absolute value is 0. So what do we mean by that? So if we were to take the absolute values and take out all the negatives and make every term positive, if that sequence goes to 0 as n goes to infinity, then the original sequence would also go to 0. Let's see what that looks like. let's suppose we have a sequence that does this. Notice this sequence goes back and forth between positive and negative. And also notice that each one, the absolute value is getting smaller and smaller. If we were to take the absolute value, this one we would get here, this one would be here, 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 here. So this sequence, the absolute value version, is monotonic because it's getting smaller and smaller and smaller. It's bounded. Turns out that it's bounded at 0, so it converges. In this one, we know it converges to 0. So if, when we take the absolute value, if that goes to 0, then the sequence in general, which is bounded between this and that, then that also goes to 0. This is basically a modified version of the squeeze theorem. If our sequence is always between two functions that have the same limit, if the limit of this sequence is 0, if the limit of this sequence is 0, then if there's a sequence that's always in between those, then the limit of that third sequence will also be 0. Now for the squeeze theorem, it doesn't always have to necessarily just be at 0. We could have a sequence, let's see, let's move it down a little bit. It's doing something like this. Let's see, scoot that down still some more. Notice the upper end of that is always smaller than that function. And let's say, if that's a sub n, let's say that as n goes to infinity, a sub n goes to 4. If we look at this bottom one, that bottom one, the bottom values are always either on or above this. If the limit is n goes to infinity of that one, let's call it b sub n. If that limit is also 4, if our sequence is always bounded between those, so bounded, this time it's not monotonic, but if it's always between those and the upper value and the lower value have the same limits, then our sequence that's in between those will also approach 4. And that's what's known as the squeeze theorem. So I'll give you several of those to take a look at. Look at convergence. Let's see. Let's look at this one. Let's call this a sub n equals that. So let's look to see, well, does this converge or diverge. If we look at this sequence, if we put a 1 in, the cube root of 1 is 1. So we get a half. If we put a 2 in, we get the cube root of 2 over the cube root of 2 plus 1, which just let's approximate that for the calculator. Cube root of 2 divided by cube root of 2 plus 1. So about 0.558. If we skip a little ways and let's get to 8, if we put an 8 in, the cube root of 8 is 2. The cube root of 8 is 2 plus 1, so 3. That's about 0.667. We skip on down a little bit further, a to the 27th. The cube root of 27 is 3. 3 plus 1 is 4. So 0.75. And notice that's monotonic. Each value is getting a little bit bigger, and a little bit bigger, and a little bit bigger. So it's monotonic. It's increasing, monotonically increasing. So if it's bounded, then we know that it's going to converge. And if you think about it, this is going to be bounded by 1. If we had that, that would be equal to 1. But that says the numerator is always bigger than the denominator. If we have something where the numerator is always 1 less than the numerator, that's got to be less than 1, so we could say it's bounded by 1. It's always smaller than that, so there is an upper limit. It's not going to keep on while it is getting bigger and bigger and bigger. It's not going to infinity. There is a maximum value, so it's bounded. It's monotonic. So this does converge. So if we want to check to see what it converges to, let's use L'Hopital's rule. So if a sub n is the cube root of n over the cube root of n plus 1, there are other ways we could do this other than L'Hopital's, but if we think of the function x to the 1/3 over x to the 1/3 plus 1, if we let that go to infinity, then the numerator goes to infinity, the denominator goes to infinity, so that's indeterminate. So if we want to apply L'Hopital's rule, we're going to take the derivative of the numerator, the derivative of the denominator. So the derivative of the numerator, we bring the 1/3 down, x to the 1 less power. The derivative of the denominator, we bring the 1/3 down, x to the 1 less power, plus the derivative of 1, which is 0. So we don't even need that. Those cancel, leaving us 1. The limit of 1 is 1. So that sequence converges to a value of 1. Does it ever reach there? No, it doesn't ever quite reach 1, but that's what it converges to. Now let's look at one or two other problems real quickly, and then I'll leave the rest of it for you for homework. One other thing that we need practice at is taking a sequence and then being able to define that sequence. as, think of it as a function, but define that sequence in terms of its nth term. So let's see. We have 1 over 1, then 1 over 2, 1 over 6, 1 over 24, 1 over 20. Notice to get from here to here, we multiply times 2. To get from here to here, we did times 3, times 4, times 5. So what could we say there? So this is 24 times 5 on bottom. This is 6 times 4 on bottom, which 24 is 6 times 4. 6 is 2 times 3. This is 1 times 2. So this is 1 times 2 times 3. This is 1 times 2 times 3 times 4. This is 1 times 2 times 3 times 4 times 5. So notice that the numerator is 1. The denominator, if this is the first term, the second one, the third one, the fourth one, the fifth one, this one is, the denominator is 5 factorial. This one is 4 factorial, 3 factorial, 2 factorial, and 1 factorial. So our sequence can be defined as 1 over n factorial. Let's look at another one. The first thing to notice is that we alternate from positive to negative to positive to negative. And the way that we can account for the changing of signs is by doing -1 to a power. -1 to an odd power is negative. -1 to an even power is positive. So this is our first term, second term, third term, first term. So usually there are two variations we use. We use either -1 to the n or -1 to the n plus 1. So if we look at this version, if we put a 1 in, that'd be -1 to the first, which is -1. If we put a 2 in, that'd be -1 squared, which is positive. -1 to the third is negative. So that gives us the opposite of what we need. So we're basically out of sequence. So if we put a +1 in, when we substitute 1 in for n, we have -1 to the 2. -1 squared is positive. If we put a 2 in, 2 plus 1 is 3. -1 cubed is negative. If we put a 3 in, that becomes even. -1 to an even is positive. When this is 4, we're odd. -1 to an odd is negative. So -1 to the n plus 1 will help us account for the changes in signs. Now we just need to figure out, well, how do we account for the values we have? Notice that the denominators are all perfect squares. This denominator is 2 squared, 3 squared, 4 squared. We don't have this written as a fraction, but if we put it over 1, yeah, that denominator is 1 squared. So we could call this, the numerator is 1. The denominator is our term, or our n squared. So a sub n is given by this. Or you could call that -1 to the n plus 1 over n squared. So either of those ways are ways of determining the nth term of our sequence. So that's the skill that we need to work on developing. If we have a sequence of numbers, can we come up with a formula to define our sequence or to set up our pattern?